Thank you for the opportunity to present the talk today. So, as the title suggests, this talk is on Dold spaces. So, first we need to know what is Dold space. Before that, uh, I want to say that Albrecht Dold introduced these manifolds in 1956 to give generators of Holmes unoriented cobordism ring. What is this? This ring is you take class of manifolds and put a equivalence relation. I will tell which equivalence relation. And for addition, you take disjoint union, and for multiplication, you take Cartesian product. And the equivalence relation is two same dimensional manifold M and N. The dimensions are N, small n, are equivalent if and only if there exist one dimensional higher manifold W such that the boundary of W equal to M disjoint union N. This is the equivalence relation. After putting this equivalence relation, this is a set, and with this operation, this becomes a ring. We call it unoriented cobordism ring. And this ring, it can be shown that this is isomorphic to some variables Wi, where I not equal to some 2 power j minus 1. I has to be of this form. This is a graded ring. And here, when I equal to even Wi, this element corresponds to the class generated by the real projective space of dimension I, because manifolds quotient relations. So this class here corresponds to Wi here. And when I odd, this Wi corresponds to classical Dold manifolds. For some PMN, this is the notation of classical Dold manifold, such that M plus 2n, this is the dimension of this manifold, this is equal to I. What is PMN? PMN is defined as you take sphere and complex positives CPN, and you identify some points by involution, that is like S comma L. CPN is collection of all complex lines in CN. So this is identified to minus is the antipodal point of S, and this is complex conjugation induced from complex conjugation on CN. So this is after this identification, whatever we get, this we called, this is the classical Dold manifold. And in 2019, Nath and Sankaran generalized this class of manifolds and studied some manifold properties like tangent bundle, stability classes of tangent bundle, stable parallelizability of tangent bundles, cobordism classes, all these things. But since our study is cohomology, we don't need to assume manifold property. So we generalize it further. And so a JDS is as follows. You take S replacing sphere and an involution alpha on S, which is free, no fixed point. and another space X replacing complex projective space, and an involution sigma replacing conjugation with fixed points. Then we denote the corresponding generalized Dold space PSX, which is defined as S cross X by X quotiented by Sx identified to alpha S, which is free involution alpha, and sigma X. So now from this definition, one can construct a lot of examples, but in particularly, we will be looking at this particular example, which is PSM cross CGNK, complex Grassmannian manifold, which consists of all k-dimensional complex planes in Cn, and this is sphere. This is SM cross CGNK modulo the relation. The relation is S, and you take a complex K plane L. This is identified to minus L, minus S, L bar. Okay. So now our target is to study the cohomology ring of, okay, let's call this manifold PMN in short, PMNK. Sorry, L bar. Yes, L bar. Okay, so in Cn, if you have a subspace L, and in Cn to Cn you have a complex conjugation. If you apply that to L, if you restrict it, you get a new subspace, right? That is L bar. Okay. So we want to see a result on the mod 2 cohomology algebra. This. And this cohomology algebra is generated by some Stephen-Whitney classes of certain vector bundles over PMNK. So what are those vector bundles? So those vector bundles are, okay, so we have gamma NK, we denoted in short gamma, and beta NK, beta over CGNK. We have two vector bundles. This is the canonical complex K plane bundle, and this is N minus K plane bundle over CGNK. And from these two vector bundles, we construct new vector bundles gamma hat and beta hat on PMNK. Yes. So the construction, let me tell you the construction a little bit. So we have this thing, CGNK 2. We have sigma, that is a bar. L goes to L bar. And we have total space of gamma. We have again sigma hat, again induced from complex conjugation. And since fixed sigma is not equal to phi, it has fixed points. So this we can think of at 0 sections of sigma hat. So fixed sigma hat also not equal to phi. So similarly, when we are able to replace X by CGNK, we can replace X by total space of gamma also. Similarly for total space of beta. So then we can form this construct. SM total space of gamma, SM cross CGNK. And we can go modulo by the relation S comma E identified to minus S comma sigma hat of E. we can go modulo by the relation S comma I. So let's call this map P. Then P of E is in complex Grassmannian. This is minus S comma sigma of P. And this is equal to the total space of our new vector bundle gamma hat, and this is PMNK. And this is S comma E maps to S comma PE. Okay, so similarly, now we have gamma hat. We can similarly have beta hat. And also one can prove that the trivial line bundle epsilon, if you take its hat, it is isomorphic to the trivial real line bundle plus twisted line bundle. Total space of twisted line bundle is SM cross CGNK cross C modulo relations. That is S E T identified to minus S L bar minus T. So it is easy to see that gamma plus beta equal to n epsilon C. This is K-plane bundle, this is n minus K-plane bundle, and this is just the perpendicular bundle to this. So you get n times Whitney sum of trivial line bundle. And if you take both side hat, it turns out that hat can split in this case, and we get gamma hat, beta hat, and this is isomorphic to this one. So we get epsilon r plus, sorry, n epsilon r plus n twisted line bundle. And then we apply total Stephen-Whitley polynomial. From this we get this relation. This is this thing is nothing but one plus first Stephen-Whitley class, of course there will be T, first Stephen-Whitley class of gamma hat plus T square, second Stephen-Whitley class. In this way up to sometimes it will become 0. This is called Stephen-Whitley polynomial, total polynomial. And then we take this term, this side only. Then we can write beta hat T equal to 1 plus whole power n gamma hat T whole inverse. Okay. And if you simplify it, I mean, one can write this as Aj T power j, where Aj is a homogeneous polynomial of degree j in the variables first Stephen-Whitley class xi and omega I of gamma hat. I is varying. Also, little more simplifying these things, one can get rid of the odd dimensional. So we only consider even gamma hat. Okay. After this, we are ready to state our result. That theorem This was uh, obtained in a joint work with Parmeshwar and Sankaran. The statement is the mod 2 cohomology algebra of PMNK is isomorphic to Z2 Y and W even hat. This even the number of the set of set where even varies. This even also varies in the same set. Just to simplify things, I'm writing this way. So this is modulo the quotient, uh, modulo the ideal m plus 1 a to j of y and hat, where this y corresponds to first CP20 class of Xi and corresponds to okay. Okay. So this is one. This is mod 2 cohomology algebra, and this thing was done actually in more general setting. This is a manifold. In our case, it was not manifold. A sim was considered to was replaced by some arbitrary paracompact Hausdorff topological space S with a free involution alpha, and complex Grassmannian was replaced by any arbitrary complex flag manifold CG nu. Okay. Okay, and then we have time. 5 minutes, 3 minutes, 4 minutes. Okay. So we computed some integral cohomology groups uh, of PM nu, and also the cohomology algebra of here we will again say in particular case PMNK in this coefficients Z2 half, sorry, Z half. Basically, we take the coefficient ring R where 2 is invertible. Yeah, it is enough to show here. Okay, so some notations. So we have gamma nk, beta nk earlier discussed, and I denote C even all the even charm classes of this and this both. C odd I denote by C odd all the odd charm classes of gamma nk and beta nk both. Also, UM is a generator of HM, SM, Z. Okay. Then this R is isomorphic to this thing is isomorphic to. Okay, I won't say. So this is this we can write as. So I won't say about this ideal for now, but I will say what are the generators of R. This R is generated by when M equal to even. The generators are C odd. Odd is varying. C odd is odd Chern classes of gamma and K and beta and K. And C even, C odd, C odd. And when M equal to odd, we have the generators C even, and C odd, C odd multiplied. So consider this as one variable. Yeah. These are the generators for R, and due to time constraint, I won't say about the ideal. That's all. Thank you.